Hello friends, good day. Today I'll be talking on the well-known dilemma bias variance trade-off. The bias variance problem is the conflict in trying to simultaneously minimize these two sources of errors that prevent supervised learning algorithm for generalizing beyond their training set. So we train our learning algorithm on the training set. Now when we try to generalize it, when we try to predict based on a unknown value, which is the test data, we face errors. The bias error is an error from erroneous assumptions in the learning algorithm. High bias can cause an algorithm to miss relevant relations between the features and target outputs, causing underfitting. So when bias goes up, we face underfitting. The variance is an error from the sensitivity to small fluctuations in the training set. High variance may result from algorithm modeling the random noise in the training data, causing overfitting. When variance goes up, we face overfitting. We tend to model the random noise in our model. So this is the case with model complexity. As model complexity increases, the bias goes down but variance goes up. And when the model complexity is low, the bias is high and the variance is low. In total, the curve is like a parabola, and we need to find the point that minimizes both bias and variance. Bias or bias plus variance, something like that. The bias variance decomposition is a way of analyzing a learning algorithm's expected generalization error with respect to a particular problem as a sum of three terms: the bias, the variance, and a quantity called the irreducible error resulting from noise in the problem itself. So, total error could be written as the sum of bias square plus variance plus the irreducible error sigma square. So this is a picture with high bias and low variance. The model is missing the actual data. The model is unbiased. The model is biased. Low variance is the expected situation when the data is centralized to the as per the model expectation, and the variance is also low. with low bias, high variance, the model expectation is right, but the variance is high and the prediction errors has gone outside the control. With high variance and high bias, the model is both out of bias and the variance is high. So these are the four cases where the expected case would be the low bias, low variance case. Some math behind: if you consider the total prediction error, which is the expected value of y minus the model prediction f hat x d whole square, is bias square plus variance plus sigma square, the irreducible error, where the bias is expected value of the model out compared to the model itself. Variance is the expected value of the model minus the expected value of the model whole square, and the sigma square is y minus fx whole square, the irreducible noise. So mathematically, the total variation in data could be written as the sum of bias square plus variance square plus sigma square. A bit of human learning. While widely discussed in the context of machine learning, the bias variance dilemma has been examined in the context of human cognition, most notably by Gard Gigerenzer and co-workers in the context of learned heuristics. They have argued that the human brain resolves the dilemma in case of the typically sparse, poorly characterized training sets provided by the experience by adopting high bias, low variance heuristics. But we first make the bias, try to make the bias zero, make the model unbiased, and then try to reduce the variance. But human learning experts are talking the other way, high bias, low variance heuristics. This reflects the fact that a zero bias approach has poor generalizability to new situations and also unreasonably presumes precise knowledge of the true state of the world. The resulting heuristics are relatively simple but produce better inferences in a wider variety of situations. They are praising high bias, low variance models. I'll stop here. The entire article is based on Wikipedia Wikipedia content. Like, comment, share, subscribe my video. I'm available for one-to-one sessions too. Thank you.